Cool. Okay, so let's get started. Hello, everyone. Thanks for joining the AI for Health webinar. I'm Jimeng Sun. I'm a computer science professor at the University of Illinois, Urbana-Champaign. I'm the host for this webinar, and this will be recorded and shared in our YouTube channel later. And so today I have a very special speaker. I'm very thrilled to introduce the used to be rising star, but now it's a superstar in AI-driven biomedical research, Professor Sheng Wang. And I mean, instead of going through his amazing paper and research records, I want to actually start it to say that Sheng's journey actually started from UIUC, where he earned his PhD in computer science, which laid the foundation for his groundbreaking research innovation later, I would say. And he then went to Stanford School of Medicine, I guess, right, to spend some time there, and then joined UW as an assistant professor in computer science. And Sheng is really kind of at the forefront of generative AI for multimodal biomedicine and tackling a very challenging task of integrating imaging, omics data for biomedical research, I mean, discovery. And his cutting edge research has led to many amazing work that he will talk about today, including GigaPath, pathology foundation model that can analyze large scale imaging data. Then this new work I saw on his abstract, OCTCube, a 3D retinal imaging model that redefines disease prediction, and this BiomedParse, and also an amazing effort for a unified nine major biomedical imaging modality. And so his research isn't just it's not theoretical, it's making a real world impact with has been adopted by various of medical institution including UW Medicine and Providence Genomics. His works has been published in many major venues including Nature, Nature, Biotech, and and science, and so on. So without further ado, let's welcome Professor Sheng Wang. Thanks, Sheng.
Thank you. Thank you, Jimo, for the great introduction. So today I'm going to talk about generative AI for multimodal medicine. And I would like to make this talk pretty interactive. You can feel free to interrupt during the talk or leave question in the chat. I can see the Zoom chat during my talk. And I'm going to focus on two things. First is the generative AI. What kind of new biomedical application, biomedical tasks that traditionally cannot be handled by traditional AI, like deep learning, but now can be solved by generative AI? And the second thing I'm going to focus on is multimodal. So what kind of task we can model now by using a multimodal framework that cannot traditionally be addressed by a unimodal framework? First of all, I would like to talk about four different paradigms or four different stages in AI for medicine. The first one is very well known, deep learning. Deep learning has been very successful on many different applications in biomedicine, but the limitation is that for deep learning, we need to develop one model for one task. So for example, here are pathology images. I want to predict subtype, I want to predict survival, I want to predict treatment. They are all on the same data set, same patient cohort. But if we want to develop deep learning model, we need to have different model architecture, different training algorithm to handle those different tasks. And then 2 years ago, actually 3 years ago, people have this very exciting idea called the foundation model, where we use one model to solve many different tasks. And the most famous one is ChatGPT, which is a foundation model that can handle many different tasks involving text data. Here, people also consider developing foundation model to handle, for example, pathology data. And this model can be used to solve many different downstream applications. And we often use one model to solve even tens or even 100 applications, just use one model. And then there's a new trend multi-modal foundation model. This time, not only in the output space, in the input space, we also try to consider different kinds of data. For example, we can use one foundation model for cancer diagnosis or cancer prognosis. And this model not only train on large-scale pathology image, but can also jointly train on large-scale CT image, large-scale MR image, and even genomics data. So using one model to handle different kinds of input modality, and then this model will be used to process different downstream applications. And this will be the focus of my talk today. And last year, there's also a new trend called the multi-agent. This time, people use one framework to integrate multiple foundation models. Each foundation model could be responsible for one thing, like one foundation model for handling pathology image, and another foundation model for handling EHR, and another foundation model for handling maybe genomics data. And these foundation models collaborate and work with each other, just like lots of doctors with different expertise stay together to work on a very challenging medical case. So today I'm going to talk about the multimodal foundation model part, but then also briefly talk about some multi-agent work we are currently working on. First of all, why do we need to develop multimodal foundation model for medicine? Because medicine is inherently multimodal. Take diabetes example. Diabetes is a pretty common disease, and we can see signal all over the body. We can use retina to diagnose diabetes. We can see signal from heart, see signal from knee. We can even see signal from the teeth. So we can use different aspects, different kinds of data to diagnose diabetes. And this justifies the needs to have different kinds of medical tests, different kind of medical procedure, which will actually generate different kinds of medical data. And these images, they are actually very different. We cannot just see them all as images. Because from a machine learning perspective, they need to be handled by different image encoder. It's not like general domain. We have cat, dog, car, different kinds of images, but all these images can be handled by the same image encoder. In medicine, for different kinds of biomedical images, we need to use different image encoder because some of them are 3D images, like CT, MR, some of them are 2D. Some of them are very large images. We need to specially design some framework architecture to handle them. So this means that they are very different. We need to process them separately and then use a joint multi-modal model to handle all of them. And then later, if we also want to consider text data, genomics data, then there will be even more modality to consider. That's why we need to develop a multi-modal model to handle this kind of very complicated heterogeneous data for diagnosis. This is the background. And today I'm going to talk about 3 recent works from my lab. The first is a pathology foundation model. The second is a 3D retinal foundation model. And these techniques can also be applied to other kinds of 3D medical images. Finally, I'm going to talk about a multi-modal foundation model, which use one model to handle 9 different image modality, including CT, MRI, ultrasound, pathology, 9 different biomedical image modality handled by just using one model. So first of all, let's take a look at the pathology foundation model. The pathology image, in my mind, is the most challenging one to handle by AI model. Why? Because pathology images are too large. So this is a pathology tissue, where we cut the patient and then take a tissue out of the patient body. It seems to be very small, which you can put on the finger, but if we want to see the detailed cell structure, organization, the tissue morphology, we often need to do a 20 or even magnification, which makes this image as large as 100,000 by 100,000 pixels. So how large is this 100,000 by 100,000 pixel? If I print this in a paper, this paper will be as large as a tennis court. So just this very small pathology image, if I print it to see all the cell structure details, it will cover the entire tennis court. And then this is the image we often handle by existing deep learning model, like the ImageNet or internet image, classifying dog, cat, different animals. Those images are very small, 256 by 256 pixels or even smaller. If I print them, they are as large as a tennis ball. So this is the mismatch. Existing AI architecture, hardware, software, existing AI algorithm, they are often developed to handle this kind of small image as large as a tennis ball. Now, if we want to work with pathology image, we need to scale them to be as large, to handle images as large as a tennis court. This is a long-standing problem that has actually slowed down the research in pathology for many years. But we found that the underlying challenge and the underlying solution here behind this kind of large-scale pathology images is actually very similar to the problem behind ChatGPT. So they seem to be two very different domains. ChatGPT is text data, question answering conversation, but pathology image is like cancer image, two very different domains. But the underlying solution and the problem are actually the same. So ChatGPT, we know that they are very good at handling very long documents. We can send ChatGPT a PDF, and then ChatGPT can provide a very nice, very concise summarization of this PDF. This is called the long context modeling ability that generative AI can do very well. The traditional AI, like deep learning, may not have a focus on this. And then we think this kind of long context modeling idea can also help us address extremely large pathology image. Our idea is to convert a very large pathology image into a sentence. Now, this sentence, which is a very long sentence, the basic element in this sentence is no longer a single word or single character. It's actually a small image that can be handled by existing deep learning algorithm, like a 256 by 256 image. And then we use long context modeling ability to model this long sentence to capture the global information within this whole slide image. So we use a model called the LongNet architecture that can handle very long sentence with even billions or millions of tokens to model this kind of very long pathology, very large pathology image. So this is the high-level idea, and this is our deep learning model architecture. We have two kinds of encoder. One is a tile encoder, like what traditional deep learning computer vision algorithm can do to model this kind of small image and to capture the local information. And then our novelty is to also use this slide level encoder, which is a LongNet architecture to capture the global information on the entire slide. And then the model will be able to make diagnosis both based on the local information and also based on the overall global information. Based on this model, we published the first whole slide foundation model for pathology called GigaPath. This is a collaboration among Microsoft Research, Providence Genomics, and the University of Washington. So this model is published in Nature last year in May, and we are excited to see that we got almost 200,000 model downloads per month, a Hugging Face. And lots of those downloads are from other countries out of US, where traditionally do not have strong training for pathologists. Now, everyone over the world can use our model to analyze their own pathology image. And this model is completely free, open source, free for commercialized use, so everyone can use it for their applications. So let's see what we learn from our model. The first thing we learn is that one foundation model can fit all kinds of data. This is slightly different from the traditional thoughts on cancer, where cancer should be highly heterogeneous, then we should have a different model to model different cancer types. We actually used one model to model 15 different cancer types. And this model is trained from 30,000 patients from 28 hospitals, cover 140,000 pathology slides. Each slide, again, is 100,000 by 100,000 pixels. So this is a very large data. And by training one model to cover many different cancer types, this model can actually have the power to generalize to many different cohorts, different patient population. And we can reach the best performance on 25 out of the 26 tasks. Let's see what tasks we did. The first set of tasks is cancer subtyping, where I give a pathology image. I do not provide anything else to the model, like the patient age, patient gender, or patient other family history. I don't provide anything else. Just by taking this pathology image, the model is actually be able to classify our ovarian cancer patients to 6 specific subtypes within ovarian cancer. This is very important because cancer subtype is a strong indicator for the potential treatment, for the potential survival, and then this can guide the clinician, guide the oncologist to make the right treatment plan. And our model can do very well. And even on quite a few cancer types, we can reach almost zero point 0.9 accuracy. So there it's a six class classification problem. So random guess will only be one over six. And our model, by only looking at the pathology image, can get almost 19% accuracy on this problem. The second set of tasks we did is biomarker prediction. Now, this time, given only a pathology image, we want to predict whether this patient will have a mutation in a certain gene or not. This is a strong indicator for the specific drug we are going to use to treat a patient. Based on a specific gene mutation, we can choose the right target therapy. And our model can do well on 17 out of the biomarker. And then in this way, we can directly predict treatment based on this pathology image. So actually, the two tasks I just mentioned, subtyping and biomarker prediction, they are all related to treatment prediction. And treatment prediction is our ultimate goal. Given pathology image, we want to predict what should we do with this patient. Should we do chemotherapy, radiotherapy, or which specific drug should we prescribe to this patient? We found that this task is very challenging. Directly predicting treatment is very hard from pathology image. Because the data is very noisy, and because the data is still limited in terms of those treatment label. We have good subtype label, we have good biomarker, but the treatment label, we don't have high quality and large scale treatment label. And then to solve this problem, we use another generative AI idea, chain of thought. Chain of thought, the key idea here is to decompose a very complicated task into many small subtasks. Here, I give an example of chain of thought by using a very simple math problem. This is a math problem counting how many tennis balls here after certain operations, which seem to be very trivial to human, but actually standard Gen AI model like ChatGPT cannot provide the right answer for this, even for this very simple question. But if we provide the procedure, like how we can derive this answer step by step, we tell ChatGPT how to solve this problem step by step, then ChatGPT can correctly solve this problem by following the same procedure. So the same model, same question, now ChatGPT can provide the right answer by following this kind of step-by-step instruction. We want to use the same idea to do in medicine to do treatment prediction. So now the problem is how to decompose the complicated problem of treatment prediction into many small steps. And this kind of chain of thought idea has not yet been applied to medicine. Our idea here is to use clinical guideline as the chain of thought. This is a clinical guideline from NCCN, the National Cancer Network, where the best cancer experts, they review lots of cases, review lots of literature, and then come up with this guideline. For this guideline, from a patient profile, for example, pathology image, the guideline first asks to determine the subtype. And then, based on a specific subtype, the guideline asks the doctors to determine the biomarker. And then, based on the biomarker, the guideline will guide the doctor to a specific treatment. So we use this guideline together with our foundation model to predict treatment. So first of all, take a pathology image, we predict subtype as suggested by guideline. The subtype will be predicted by our model. Once our model predicts subtype, we know we should go here. And then we ask our model to predict biomarkers. And once we know the biomarker, we will again follow the guideline and then go to the specific treatment. So this can be regarded as a human-AI collaboration. And I think this will be the future of AI for medicine, where AI model will never replace the doctors. Experts, oncologists, doctors will derive this kind of guideline and instruction, and the AI model will make decision on each small step. And then we can think AI model as a lab test. It's like a blood test, a CT test, or a pathology or MRI test, where doctor can order in real time. If there's some information oncologists need to help them do diagnosis, they can order an AI model to predict a specific subtype, specific substep, and then help them reach the final goal of disease diagnosis. Okay, this is the first part of my talk. I would like to pause for 1 minute and see if there's any questions from the audience.
Sheng, this is very interesting. Can you say more about this slide on the part? Do you have some difficulty or challenge in parsing NCCN guideline to create those necessary, I guess, treatment
Yeah,
procedure? Yeah.
yeah, that's a very good question. NCCN guideline is like a large PDF means with like a 50 or 60 pages. And we at beginning with ChatGPT to process it, but ChatGPT can actually with GPT to process it, GPT cannot go through multiple pages in the PDF. So we actually do it manually, mostly manually, with some help with ChatGPT. So parsing this is actually challenging for ChatGPT.
And the output of this parsing is like some kind of a decision tree.
JSON, yeah, we use a JSON file decision tree, if else rule to do it. Once we have the JSON file decision tree, then model can understand it correctly.
Okay, that's that makes sense. Thanks.
Great. Okay. Any other questions? Yeah,
Hi,
you can.
hi,
Yeah,
Sheng.
please.
Yeah, my name is Luigi. I have a question on the chain of thought modeling part. So, so here, it seems that this guideline is a sequential procedure. Does this mean uh, any sequential clinical decisions will entail the good application scenario of chainsaw of COT, or you have additional knowledge that can be digested by the model so that the chain of thought model can digest those knowledge in addition to the the sequence of the data. I'm not sure if you
Yeah, yeah, that's a very good question. First of all, I think any sequential decision, um, often followed by doctors, will naturally be chain of thought for foundation models. This is what I think. Maybe there should be
I
some
see.
reformatting. And then can you repeat your second question regarding the
Yeah. So my question, I guess, is a follow-up. So in addition to the sequence characteristics of the data, what kind of additional characteristics of the data that makes the chain of thought applicable to these decisions?
as long as it's a tree or a sequence, then it definitely can be
I see.
applied to
I
chain of
see.
thought.
I see.
Um,
I see.
in foundation model, well, all the days, not even foundation model, in all the days of BERT or GPT-2, there's another technique called the prefix tuning or soft fine tuning. That's something happened before in context learning, where you can append an embedding vector before the sentence embedding to do some joint fine tuning, and the model will try to learn that embedding. This could be
I
a
see.
more, although not used in NLP anymore, but
I
in
see.
medicine, that could be a universal general solution where if you have some other embeddings from some other application, you think it's a high quality and not covered by the foundation model, you can always pull that
I see. I see.
to train the model. That's like in context learning, although not explicitly as a sentence or an image.
I see. I see. I see. Thanks. Yeah, I
So
got
yeah,
my
I think
answer.
there's lots of things to do to design channel sort in context learning in medicine. That's actually our focus, and there's little little work has done in this area. But I think that will be the focus in medical foundation model, just like how it is the most important thing in general foundation model now.
I see. I see. Okay. Thanks. Yeah.
Thank you. So there's a question in the chat, which is very similar to Gmo's question. How did you pass the graph or flow chart in the guideline? It's based on LLM parsing. Or so we actually there are two steps. From PDF, we want to extract all the if else rules. If this subtype then go to which biomarker. So this is first step, extracting those kind of if else rules from the PDF. This step we actually do it mostly manually. We try to use ChatGPT, GPT 4.0 to do it, but the performance is not good. So we mostly do it manually. Once we have if else rules, we don't necessarily need to build a graph. We don't need to show the graph to our foundation model. we just write our own code, like every step, how should we query the graph? How should we query the foundation model based on the graph? What function should we use from the foundation model based on graph? This is kind of like a multi-agent system, but it's not like a real, like a collaborative agent system. But just every step in this graph, we will call a function in our foundation model to do the specific task. So again, lots of manually coding, manually labeling here. We didn't use any ChatGPT something here.
Thank you.
Thank you. Yeah, so that's the first part, and now I'm going to talk about second part. First part, we talk about the pathology foundation model. Actually, this is already a challenging for general domain computer vision. And there are another kinds of very prevalent medical imaging that cannot be handled by general domain is 3D model, 3D imaging. So general domain computer vision, it's a very, very productive area. But the problem is that it's mostly 2D imaging because all the training data is either ImageNet or internet images. They are inherently 2D. There's some 3D works, but mostly about video. And video is actually, it can be considered 3D, but still slightly different from the 3D imaging we see in medicine. And in medicine, there are lots of 3D imaging, CT, MR, OCT. And 3D imaging is more informative than 2D. Like CT is often more informative than X-ray. And MR is also a very informative thing. So how can we build foundation model to handle 3D imaging? That's a very important problem. Here we focus on OCT, the retinal disease. And here, this is a patient's retina. Here I show a real patient with age-related macular degeneration to help you motivate the problem of modeling 3D instead of 2D. And then this is the OCT volume. We take a very small region from here. And this OCT, 3D OCT, we can think it as many different slices of 2D image. 3D OCT volume often have about 60 2D slices. And there's a state-of-art model called RedFound. RedFound only look at the center slice, the center of the 3D, because modeling 3D is very challenging. So RedFound thinks maybe it's a good idea to just look at a center slice, because most of the signal is often in the center slice. For this patient, when we look at the center slide, we did not see any age-related macular degeneration signal. But if we go a few slides lower, and then on this slide, we see the signal of AMD, age-related macular degeneration. And you can see the challenge here. The disease signal is very, very small, just a few pixels compared to the entire 3D volume. It's a very small pixel. For doctors, it's very hard to see. And for AI model, it's even harder because it's just a small pixel among this very large 3D volume. So based on this intuition, we think it's necessary to develop a 3D foundation model that can see lots of 3D images and set up as an initialization or foundation for future diseases, especially for some rare retinal diseases. Here we use architecture. We actually try many different architecture. And turns out that this mask autoencoder based architecture has the best performance in our pre-training pipeline. And another important thing we do is to use flash attention. 3D volume is very large. It's very hard to put a 3D volume into GPU memory due to the batch size limitation. And the successful pre-training needs a very large batch size. So we use flash attention to help us optimize the GPU memory, the optimization procedure. And the high-level idea is similar to our pathology. We convert a 3D volume to a long sentence of small cubes. And then each small cube, you can think it as a word. And then the entire pre-training could be similar to pre-training of text data. Okay, so this is our pre-training architecture. And then we collect OCT data from 26,000 patients. Each patient will provide almost 2 retina, one for right eye and one for the right eye, one for the left eye. So this is a training of very large data set 3D foundation model. And this is a collaboration between University of Washington with Dr. Cecilia and Aaron Lee, and also with Genetech with Dr. Miao Zhang from Genetech. Our model achieved the best performance against 2D model on all the 29 tasks for this OCT-based retinal diagnosis. So let's see what we can do. The first thing we can do is to do a very accurate prediction on 8 different retinal diseases. Those are 8 different retinal diseases, including AMD and many other diseases. And our model, OCTCube, is better than a 2D model, and we implement 2 kinds of 2D model. One is the original 2D model that only considers the center slice. We also implement another 2D model, which embed every 2D image, every 2D slice, and then take the average of the 2D slice. So this RedFound actually also used the 3D data, the same data as we did, but they didn't holistically or comprehensively model the entire 3D volume. So our model is still better. This means that considering the entire 3D volume is very important. In addition to accurate prediction, we can also do interpretation. This is again the OCT slice from the bottom layer to the top layer for the AMD patient. Now we want to see which region did the model look like to make the prediction. This is the region RedFound focus on. This kind of red pixel is a salience map. Red pixel means the region the model looks like. And we found that for many times, RedFound is actually looking at regions fall out of the retina area. Like this part and this part, they are not even within the retina area. So the model, although can provide good prediction, may not actually using the right part of the image to make prediction. In contrast, our method, this is interpretation. We can see that the region we think are important often fall within the retina region. And we also see a good consistency, which means that for 2 slices, very nearby slices, like this one and this one, or this one and this one, they actually are, the model actually looking at a similar region. So this means that the model can understand the entire 3D volume holistically. And this kind of interpretation can provide doctors additional information to make the diagnosis and to provide additional information for doctors to evaluate the performance of our AI model. We also did cross-cohort prediction, where the model is entirely trained on patients from Seattle, mostly in Washington, mostly in Seattle. And then we test the model on other cohorts, other collection from Duke, Minnesota, Johns Hopkins, and NYU. On all those kind of cross-cohort setting, we outperform the 2D model we significantly outperform the 2D model. This shows the generalizability of 3D model. And then another very interesting thing about OCT prediction is the cross-device prediction. These are 2 retinal images of the same patient, same eye. Okay, they are the same patient, same eye, acquired by 2 different devices. We can see that these 2 images look very different. They have different angle, different shape, but they are actually the same eye. This is because the devices are very different. So you can imagine if a model is trained on the first device and then later be applied to another hospital, acquire data using the second device, it will be very challenging for the model to generalize. And then we test this kind of scenario where we train on the first device and then test on second device. In this setting, we still outperform existing approaches with a large margin. We also test another kind of device where we still train on this kind of device and test it on a third device. We also can show very good performance. This is because the 3D model look at the entire volume rather than 2D model, which look at the individual size. If we look at the entire volume, the model will be more robust to this kind of different angles, different shape, different rotations. And then the model can focus on the specific disease pattern. And then we also use retinal, the OCT image, to predict systematic disease. Diseases like diabetes, hypertension, that we can see signal from many different organs, tissues in the human body. And by only using the retinal image, we didn't use anything else, we can accurately predict diabetes, hypertension, and many other diseases, outperforming existing 2D model. Here is an example of a real patient at UW Medicine. So this patient has diabetes. During the first visit, the 2D model did not identify diabetes. But meanwhile, during the first visit, our 3D model successfully predicts that this patient has diabetes by looking at a few other slices and then find this kind of signals. So the 3D model successfully predict this patient has diabetes. And after 1 year follow-up, this patient has lots of diabetes signal here, and then the 2D model also successfully detects diabetes. But our 3D model, again, can detect it 1 year earlier. So this kind of 3D model also enable early detection of this kind of systematic diseases. Okay, this is the second part I would like to talk today. Again, I want to pause for 1 minute to see if there's any question regarding our 3D foundation model. Okay, great. So now I'm going to talk about this third work. That is a foundation model, a multimodal foundation model integrating 9 different image modalities. We actually did some multimodal analysis in our pathology foundation model and retinal foundation model as well. In our pathology foundation model, we try to integrate pathology image and pathology text. In our retinal foundation model, we also integrate OCT image and IR image. They are 2 different views of the same eye. But I will say they are still limited, although they show pretty good performance, but they are still limited because the information we model here are very redundant. Pathology image and pathology text, they are redundant because pathology text, pathology report is a description of the image. And here, OCT and IR image, they are 2 different views of the same eye. So it's very redundant information. It's relatively easy to model. What is more interesting is to model all these kind of images from the human body. And then they are very complementary, very different. Some about the eyes, some about the teeth, some about the brain. They are very different. But to train such model with so many different images is very challenging because it's impossible to get any training data that we can collect all those images. We cannot find any patient who has done tests for all those kind of medical procedures. And then how could we train such a model? Another challenge is that in general domain, those kind of multimodal framework is mostly limited to 2 modality based on clip architecture. Here, if we have more than 2 modality, if we have 9 different modalities, how can we use a deep learning model to integrate all of them? So this is the challenge for us to integrating multimodal images to build one foundation model that can handle many different images. Our solution to this is this is our solution to handle this problem. We build one foundation model for each modality, and then we project different foundation model into the same space. This is actually inspired by a language called Esperanto. Esperanto is a constructed language, it's not a real language. But the idea is that if everyone can speak Esperanto, then we don't need any translator. Everyone can just translate their language to Esperanto and then communicate using Esperanto. So this is a very nice idea. And we want to do the same thing for biomedical imaging. How can we translate all kinds of biomedical imaging to a shared space? And what should that shared space be in medicine? In our recent paper, it's a method called BiomedParse. We use, in a recent work called BiomedParse, we use human language as the Esperanto to integrate 9 different image modalities. Those are the 9 different image modalities we want to integrate. CT, MR, X-ray, they are very different. Some are 3D, some are 2D, some are very large, some are small. But there's one commonality is that every single medical image has a medical report. Doctor will write about what's going on in that image. And then for every single biomedical image, we can use the image text association to project that image to the text space. In this way, human language is the Esperanto. We project all the images to text space using the human language. And then 2 images will be close to each other in the text space, not because they are both CT or both MRI or both pathology, but because they are talking about similar patients. So one could be a MR image, one could be a pathology image, but they are about the same kind of cancer type patients. And then they will be close to each other in this text space. To build this BiomedParse model, we project 6.8 million images. Every image has some text, either description, segmentation label, or notes. And then those images from 9 different modalities, we project them into the same text space. This is what our model learned. Okay, so now in the text space, I can use the text space to generate the image back to see whether our model can actually understand the text in the image. Here, I type in something like a liver in abdomen CT. I didn't provide anything else. And then from the text space, by mapping back to the image space, this is the salience map or heat map we can see. We can see a clear shape of liver. And then here, by only adding one additional word, vessel, liver vessel, and then from the text space to the image space, the model immediately generates liver vessel rather than the liver shape. So this means that the model can understand the text image correspondence very well, and the model is very sensitive to this kind of change in the text space. Here's another example. I change liver to kidney, I change liver to pancreas. The model also correctly visualize the shape of those kind of tissue. And then there's another two examples from pathology. One is called inflammatory cells, which are often close to each other in the pathology image. The other is called the neoplastic cells, which are often spread over in the image. Our model also identified this kind of pattern. Neoplastic cell, we see distribution all over the image, while inflammatory cell, we see very focused distribution in one part of the image. This is an expectation of the embedding space, showing that our model can very well understand the text. So based on this, we published this paper in Nature Methods 3 months ago. And this is a foundation model that can do segmentation, detection, and object recognition on 9 different biomedical imaging modality. This is again a collaboration with Microsoft Research, and the model is completely open source, free for any commercialized or research purpose use. So we have those papers, we have developed tools and put models on Hugging Face and also release codes on GitHub. But one thing we try to push forward very hard, especially during our collaboration with Microsoft, is actually to deliver tools that doctor can immediately use. For this project, this is what we deliver to the doctor. Not a tool or code or software. We want people to do coding-free explanation of our exploration of our model. We developed this web server. And here's a video. Let's see if I can play this. Okay, so this is a video of what our server looks like. The user can upload here, the user upload a CT image, and the user want to know whether there's a nodule in this CT image. And then they can simply type lung nodule in this chest CT, and after immediately, our model will be able to find the lung nodule, circle it, label it, and tell user, we found the lung nodule on the right of the image. In this process, the users are not restricted by the text. They can type anything freely, like in a search engine, Bing search engine, Google search engine. They can type anything, and this kind of text modeling ability is powered by large language text model like GPT or BERT. They can type anything they want, and then our model will be able to understand it and then find it here. User does not need to provide any supervision, or they don't even need to read the image. Now, this is another example. This is a pathology image, and most people do not have background in pathology. And now I want to see what cell types are there. And I don't even know the name of the candidate cell types, like neoplastic cell, T cell, B cell. I don't even know those vocabulary. I can simply say, get all cell types. And then this is the output of our model. The model, again, will immediately find 3 different cell types, color them, label them, and tell the user, we found those 3 cell types. This can be done very efficiently without any domain knowledge. Users do not need to understand or even read their image. And we can process lots of images in real time by saying, get all cell types from all those pathology images. And this kind of results can be generalized to not only pathology and MR or CT, but the 9 different image modality. It's a universal solution for many different image modality. And it can be very efficient and highly accurate. This is a pathology image, and the pathologist will spend lots of time to label, circle every cell here, and mark them as tumor region or non-tumor region. So there are hundreds of cells here, and you can imagine it's a very, very time-consuming process with substantial domain knowledge. Pathology needs to label all of them. And then we send the original pathology image, which is here, to the model, and we simply ask the model to get all cell types. This is the label by our model with more than 19% consistency between our model and the pathologist annotation, and it only takes 0.2 seconds to get everything here. And the model is also, and our model does not need any bounding box. Then this makes our model extremely well on handling irregular shaped objects. So traditional segmentation approach, people need to interactively work with the model. For an image, if I want to segment something, I need to provide a bounding box. And then the model will try to find the object within the bounding box. Alternatively, we do not need a bounding box. We only need a text description. Like here, for this image, we only need to write left heart ventricle. For this image, I don't need to write lung nodule. I don't need any bounding box. And we found that this is not only makes things less time consuming, but also provide more accurate segmentation for objects that cannot be well handled by a bounding box. For example, for vessel, which is like those kind of isolated part in liver, if we use a bounding box-based approach, the baseline model will actually segment so many regions here, and the vessel is only part of it. But our model will be able to correctly find the vessel. Similarly here, if there are multiple cells, if we just use one bounding box, the model will actually segment all the cells in one box. But in contrast, we can find every individual cell using our model. So this is how we can also help with the irregular shaped objects. Based on this tool, we are now extending it to actually push forward to make it used in UW Medicine. With collaborators from different domains, I would like to acknowledge all of my collaborators from different domains like heart, cardiology, from retinal disease, from brain disease. We now call it data racing, similar to fundraising, but we don't risk funding, we risk data to help us train this kind of multimodal foundation model using all kinds of biomedical images. So this is the third part of my talk. Now I would like to talk a bit about future work and current work we are working on. So we talk about this, we mainly focus on the multimodal foundation model paradigm in this talk. And then another very exciting paradigm is the multi-agent paradigm. This is what we are working on right now. We want to build something like Microsoft 365, but for cancer diagnosis. Microsoft 365 is a full package, including everything, calendar for people to do daily business, like PowerPoint, Word for their daily work. So it's a full package of everything. And by using all of them, they can support our daily work, daily business. In cancer research, we want to also integrate all the models we have built now, and also many very exciting open source models built by others. For example, we would like to use different kinds of medical vision language model to help us analyze medical images. And if this vision model cannot provide fine-grained description, cannot provide fine-grained analysis, we will then query a more specialized foundation model, like GigaPath or BiomedParse. And if we even need more domain knowledge, like what people did in retrieval augment in RAG for LLM, we will also retrieve relevant information from other databases, like drug bank, like PharmGKB. So this is what we envision in the future. The future will be where we have all sorts of tools integrated together, and then we have a giant agent, ChatGPT or GPT-4, to learn how to use those tools to handle very complicated cancer diagnosis case. And this will be like molecular tumor board, where doctors from different regions, different areas, pathologists, radiologists, they stay together to solve a problem together. But in our solution, it will be different AI models, and then with doctors together to solve the model, solve the problem more efficiently. So we talk about 4 paradigms, and then I would like to talk a little bit about future work. What might be the 5th paradigms in the future? Gen AI developing so fast, we see big news every month or every week. There are so many exciting breakthroughs. And in medicine, what might be the 5th paradigm? So to answer this question, I would like to summarize 3 lessons we learned from Gen AI for medicine. The first one is pretty acceptable to most of the people. Medical foundation models are very accurate. They are state-of-the-art in many tasks: chatbot, conversation, medical image analysis, genomics data. Medical foundation models have shown their potential in so many different things. But the second lesson we learned is actually less well known. Medical foundation models are very heterogeneous. Here, I show the pre-training data source of 3 best existing pathology foundation models. They are the state-of-the-art model, one is developed by us, one is developed by Memory Sloan Kettering, one is developed by Harvard. So they are all pathology foundation model, very large scale. And I would say they are like a comparable, and maybe sometimes our model is based on this benchmark, and then sometimes the Harvard model is based on another benchmark. So really comparable. But the very surprising is that the training data source is completely different. Our model is trained from patients from mostly West Coast, from Washington, Oregon. MSK is trained from patients from New York, and Harvard model is trained from patients from Boston. So three very different and large-scale pre-training set actually result in very good foundation model. This suggests the possibility to ensemble them for even better performance. And then the third lesson we learn is even more striking. In contrast to general domain like ChatGPT, in medicine, less than 0.001% of existing data is used by even the largest medical foundation model. So here I have some statistics. In US, every year, it will produce at least 80 million CT. The largest CT foundation model actually only uses 100,000 CT as the pre-training set. And this is 100 CT, 100,000 collected over 10 years. Pathology is similar. In US, it will generate at least 100 million pathology slides every year, but the largest pathology foundation model is only trained on 170,000 over 10 years. So it's a very, very small amount of data, but already give us the best performance on so many different benchmarks. This is in contrast to general domain, where ChatGPT or GPT might already have used all the existing text data, human text data, internet data, book data, everything. So they need to think about how to do post-training process, how to do scaling the parameters, how to scaling the inference time. But in medicine, we are way behind. There's actually a potential to use all the data because we are using very, very small data. There's a huge potential here. But the limitation is data sharing. It's impossible to share all the data, 18 million data, in one institute or one hospital. That's impossible. The data is very large. The data sharing will introduce lots of privacy problems. And this is why we propose the fifth paradigm, where we think will be the future for Gen AI. We hope to build one Gen AI model using medical data all over the world. There's one model covering everything. And we want to do a distributed development. Every medical center, whether it's in US, in Seattle, in New York, in California, or whether it's a medical center in China, in Singapore, in Japan, in Europe, in Africa, every medical center build their own foundation model using their own data. So the data will not be shared. And then only the model weights will be shared. This will introduce much less privacy concern because all the existing foundation model, their weights are already in the Hugging Face as open source weights. So every medical center build their own model, foundation model, they share the weights to Hugging Face or somewhere. And then all we need to do is a very light mixture of experts model that can integrate all these medical foundation model over the world to one mixture of experts model. So this could be a very exciting opportunity. Then what specific techniques we need to achieve this goal? The first thing we need to do is to have accessible Gen AI techniques. So in many other countries, or some of our collaborators, not in US, we learned that it's still hard for them to build foundation model for them, even they have very high quality, large scale data. They don't know how to process the data. They don't know how to do large scale training, which architecture they should use. They also don't even have the GPU resource to train the model. So how can we develop this kind of very accessible Gen AI techniques? Just like how PyTorch help everyone to build their deep learning framework, how NumPy help everyone to build their data science pipeline. We hope to have similar Gen AI technique pipeline that can help everyone all over the world to build their own foundation model. The second problem is a machine learning problem. How to use mixture of experts to potentially integrate thousands of models. And assuming some of those models may not be so good, it should be downweighted. Some of the models should be important, it should be upweighted. And assuming it should be a personalized solution, which for a new patient, I need to determine which model all over the world I should use. For example, if this patient is an Asian patient, then I might consider I should consider more from models developed in Asia. So this should be a personalized mixture of experts model. Finally, we also need to develop small size model so that we can integrate so many models and then do inference with limited resource in a clinical setting. And if we can solve those problems to build a world model, what can we do? The first exciting application is rare disease. A disease could be very rare in a certain region or country. But if we can collect data, model, resource all over the world, we can more easily find similar patients to tackle this very rare case. Second application could be systematic disease that will need information signal over the body. And then by collecting so many data, we will be able to better understand the correlation or dependency among different diseases. And this could introduce opportunity for drug repurposing. If we found that, for example, retinal imaging can actually be predictive for diabetes or predictive for cancer, and then this might suggest that retinal drug can be used to treat cancer. So by integrating and correlating those kind of different modalities, different diseases, there could be new drug repurposing opportunities. The third thing will be imaging generation. That's the focus, that's the advantage of existing generative model in general domain, but in medicine, it's still very limited. It's very hard to generate high quality imaging. I think this is because the data is still limited. If we can collect lots of data, lots of model over the world, then we might be able to generate invasive imaging, like some imaging test where we need to inject something into the human patient body using non-invasive imaging, like a CT image. This could greatly reduce the pain of patient and also greatly accelerate the medical test we need to do. So this is all I want to talk about today. Again, I want to acknowledge all of my great collaborators with Medicine to help us support us with all the clinical expertise and data set to build these models. And I also would like to thank all of my people who found me and my collaborator co-authors on collaborating with us on so many great projects. And thank you so much. I'm happy to take questions.
Thanks, Sheng. This is an amazing talk. I mean, a lot of this are so well explained. I mean, even for clinicians, I'm sure you work with a lot of clinicians. You have to explain all this. I know we're on top of the hour. Do you just have a few minutes to stay and
I have time.
Yeah. So for the audience, if you have a question, feel free to put it in the chat, or you can just ask directly.
So Sarah asked a question about open source. All three models are open source. This one, the retinal one, if you're asking about the retinal one, so the pathology, the first work and third work are already open source on Hugging Face or somewhere. The second one is not yet, but it will be open source. We scheduled to open source it, release it yesterday, but the student has some delay. So it should be open source this week. So all three models will be open source this week on Hugging Face.
That's great. So maybe I can start asking. I mean, I have so many questions for you. Maybe when you talk about, maybe let's start with this multi-agents idea that you mentioned as the fourth paradigms for medicine. So when you presented all those different AI models, right, for different modality, use them as different kind of tools, and they can somehow collaborate together. And if you use the analogies of Microsoft 365, they are more like if you think about a set of different tools, right? Then the user, the human will use them, right, to achieve some business goal, right, to do the work. Here, are you thinking about if that for the medical domain, or like this are a set of APIs for different use cases? You put in different data modality, you can get some results. Then, but the user, the human doctor or researcher will use them. Or are you thinking about more, okay, they can actually automate, right, to orchestrate, work together to make decision, take actions without human in the loop, right? What do you have in mind in this agent space?
So this is a very good question. I think if we just provide an API, it will be like a workflow that should be pretty straightforward and let the user determine which API they would like to call among so many different models. What we are interested in developing is that we let a ChatGPT or GPT-4 to determine which API it should call based on the user requirement. Like if doctor present a medical case, just showing all kinds of images of this patient with multiple visits. and also the clinical notes and ask the question, then how we want ChatGPT to call those tools automatically. We don't want to show those APIs to doctors, so doctor need to make the decision. So this is what we are working on. I think will be a promising future here. Although it's a very challenging problem.
I see. I think that's interesting. So you're saying it's not fully automated, right? The user still will ask something
Yeah,
like a GPT to try to do some work. And then instead of figuring out what API, what model to use, understand the input output format, this ChatGPT type of engine will direct the user's question into those API called and get the data result back and present back to the user. Okay, that's interesting.
yeah,
And there's several questions. Zifeng, you want to ask your question? Or there's difference between word model and FL. I had a similar question. I said, sounds like you were talking about not just this federated learning direction, right? And more of
yeah,
some
yeah. This world model is very similar to federated learning. It's the high level idea is similar. We share parameters. We do not share data. But I think in the context of foundation model, there's much more to do, like I listed here. For example, in federated learning, training model for individual data or individual users, that's pretty trivial. Let's assume it's a simple thing, like everyone training a neural network. But for foundation model, it's actually not so easy. It's more like an engineer effort, how we can make our tool open source, easy to use, accessible, so people from like other countries where they do not have strong AI researcher can follow and use. So there's substantial engineer effort. That's also why we are trying to open source all the tools we developed it. Secondly, the mix of experts or integrate many different foundation models is very challenging because every foundation machine model is already a large model, complicated one. How to integrate many of them is still unclear, and it will need substantial computational resource to iterate over the architecture of mixture of experts to learn how to train this mixture of experts model. So this is another difference. Also, the small size model is also not a concern for federated learning because their model is often relatively small, but this is actually a concern for foundation model. So high level ideas are similar, but there are specific technical details we need to address.
Yeah, thanks. So I think maybe something different from my perspective is like federated learning, you want to train a universal model that share actually, I mean, get a weight update from different data sources. But here you may have different model weights across different data sources, and you actually try to learn some high level mixture expert models that like have make the predictions based on different model weights. So they are not actually share the same set of weights here. Is that correct?
Yes. So we can also share the weights like using every foundation model as a student, as a teacher to teach a giant student. So it's like a one student, which is our final model with thousands of teachers. And then this giant student will be the shared weight for any user in the future. That's also a solution, potential solution. So it's unclear how to do it. I think a mixture of experts at this point could be a more lightweight solution in terms of a computational resource, but a traditional or other kinds of idea from federal learning, technical idea could also be applied here, like the one you mentioned.
Thank you.
I think you probably kind of answered Benjamin's question, similar question on there. Ben, you want to clarify more, or we already answered your question?
No, the question is basically answered. Thank you.
Okay, cool.
It's a very
Thank
clear
you.
explanation.
And Sheng, maybe if you can, you mentioned there's something very interesting, but kind of known, right? There's most of the medical data are not used for model training. And one of the probably the two most obvious reasons are privacy constraint and some legal constraints, right? I wonder, do you have some thoughts on how to make use of more data for training this model, or I mean, given all this privacy laws, I mean, HIPAA, or maybe some this time of constraint, or this is mostly you have to work with clinician if they're open, then you can build those models on those data. Or what's your thoughts on this issue?
So in our experience, different clinicians have uh, different thoughts on this. Some are pretty open-minded. For example, Microsoft Azure and Amazon AWS, they can support the HIPAA compliant storage of data. So it's actually safe to upload microdata, PHI data to the cloud and train the model there. But we still don't do it because there will be another kind of regulation within UW, whether UW agrees with that or not. So I think that's still a constraint, and like it's hard to have it's like hard to have it's hard to have like a
Mm.
common sense within all the hospital or all the doctors. So we still do it case by case and that's why we're also trying to make the model smaller, more efficient. So with the limited local resource, we can still train the model.
Makes sense. So what about another thing I want to ask you? Okay, for we all work on this vertical AI model for medicine, right? So there are vertical AI model for other industry as well. And as you can see all this generic frontier model become more and more powerful every iteration. What's your take on the concern of, oh, maybe those generic model will be just good enough, right? You don't have to do this vertical AI model for medicine or healthcare. Just wait until some later version of the frontier model for generic domain. They will solve all your problem. What's your take on that viewpoint?
So I think that's actually a very good question. We are thinking about like every day to see what problem we can work on. So my take is that in text domain, generic model will be very powerful. Frontier model will be very powerful. And maybe it's hard to build a biomedical version of something that can outperform GPT. Like in Hui Feng's team at Microsoft, they have a successful model like PubMedBird, BioGPT. But when GPT keep updating, it's likely to be on par with this kind of medical specific model. So text data, I think frontier generic model will be very good. But there's other kinds of images. If it's multimodal setting, for example, pathology image, 100,000 by 100,000, ChatGPT simply cannot take it as input. GPT-4o, GPT-4v cannot take such a large image as input. 3D image, 3D CT, GPT-4v also cannot. They can only take a 2D small image. That's why there's a space for us to do some novel research there. And I think this problem will be even more severe. The frontier model will even more limited if we consider to jointly model multiple modality, a large pathology image with a 3D CT, with a 3D MR, and then ChatGPT frontier model cannot do that. Not only because there are restrictions in handling large data, but also because of their training data limitation. ChatGPT, this kind of frontier model will be trained on public data. That would be, but the ability to understand this kind of complicated medical images will require the training on private data. So I think there's a huge potential to do things in medical imaging that existing frontier model cannot catch up. On the other hand, what we did is try to use frontier models to help train our own medical vision language model. Like we can distill lots of high quality text data from frontier model using their strong text understanding ability to help improve our medical foundation model. So on image part, using our own model, on text part, using their model, then we combine them together to the medical vision language model. This is exactly what we did for this work, where we use lots of ChatGPT stuff to distillation to handle the text data. But the image is something we developed in-house.
That makes sense. Yeah, I agree. I think this multimodality seems to be still a very challenging for the frontier model, especially in this medical domain. And I know you heard it stay on for 10, 15 minutes. I don't want to take too much of your time for the day. Maybe the last question I always ask our speakers, in your case, especially relevant for our students, like if you could go back to your UI/UC days, right? I mean, when you're still doing PhD, what advice or directions or effort would you tell your younger self to do more, or if you have that opportunity?
Um, so yeah, I think maybe well, so some stories when I was at ULC, I started in ULC at 2013, and then I graduated in 2018, so 5 years as a PhD student. When I started, I was a PhD student in NLP text mining, and then after 1 or 2 years, I started to work on computational biology. That actually also suggested by my advisor, Professor Chen Xiangzhai. He
Mhm.
told me that at that time, text modeling NLP is very popular because that's the golden era for search engine, Google Bing search engine. But Professor Zhai told me to think about what might happen in 5 or 10 years, whether search engine will still be something important or search engine will be almost solved. And maybe he thinks search engine will be, uh, maybe he thinks there could be great potential in other area, and he suggests me to consider using methods behind search engine, NLP methods, to either work on education or healthcare. So to explore very different domains. And that's why I start to work on AI for healthcare and then go to computational biology, now work on those foundation models. So from my personal experience, I think for us who work in academia, we should think about maybe what might happen in 5 or 10 years rather than chasing the trend in industry. It's all about ChatGPT, LLM. Like at UW, I feel that every student now, they're all excited about ChatGPT. But there could be other problems also important, like in our AI medicine work, where we use the breakthrough techniques in ChatGPT, but use it to solve another, to do contribution in another domain. That could be also very important. So this is what I see.
Yeah, that's a very, I mean, interesting, or very valuable. If you can predict 5 years into the future, I guess at that point, probably that topic's not super, super hot yet, right? I guess it's less competition, and also you get a head start. That's how you did. Do you think that's the same advice for uh, as a early days as a faculty? I mean, that's same advice, or you think there are some other advice would you give to yourself about research or career strategy when you're just starting as a faculty member?
Yes, in faculty might be might be different from PhD. We want to have a small start, and then we want to have some success as soon as possible so we can establish ourselves. So that could be maybe different. And it's also hard to change the research direction dramatically, change it a lot in working as faculty. So for faculty, there might be more, it could be more tricky to thinking this way.
Yeah. Okay, that's great. Thanks, Sheng. This is amazing talk. I mean, we learned so much from this, and thank you for making the time and share with us your recent and latest work. And I really appreciate it.
Thank you so much. Thanks, everyone. Thank you. Bye-bye.
Bye.